A 32 billion parameter AI model is outperforming models 15 times its size at running terminal commands autonomously, and NVIDIA just gave away the entire recipe for free. That model, Nematron Terminal 32B, beat the 480 billion parameter Qwen3C coder and rivals Grok 4 on real-world coding benchmarks, and every piece of the training pipeline is now open source. Meanwhile, in one of the strangest data stories of the year, 30 billion photos snapped by Pokémon Go players are now guiding autonomous delivery robots through city streets with centimeter-level accuracy. Two massive developments today that reshape how AI gets built and how it moves through the physical world. On March 10, 2026, NVIDIA open-sourced the Nematron Terminal family of models, available in 8B, 14B, and 32B parameter sizes, along with a complete synthetic data pipeline called Terminal Task Gen. These models are purpose-built for one thing: operating autonomously inside a terminal environment. Think running shell commands, debugging system configurations, training machine learning models, navigating file systems, all the work that tools like Claude Code and similar coding agents handle today. The models are fine-tuned from Qwen 3 and work through a deliberately minimal orchestration layer NVIDIA calls Terminus 2. The model receives the current terminal screen state, outputs a JSON object with proposed keystrokes, and an agent loop running inside a sandboxed Docker container executes those keystrokes in a tmux session. The model never directly touches the terminal. It proposes actions, and the orchestration layer carries them out. The real breakthrough is the data pipeline. Training terminal agents has always been painful because you need two things that are hard to get: diverse task prompts with realistic dependency files, and step-by-step interaction trajectories that capture how an agent should navigate complex workflows. Human demonstrations are slow. Synthetic generation through existing LLMs is expensive because every single turn requires spinning up a fresh Docker environment. NVIDIA's Terminal Task Gen solves this with a coarse-to-fine generation approach that scales training data without the cost explosion. And there's a counterintuitive detail in the methodology. They kept the unsuccessful trajectories in the training set. Failed attempts, dead ends, error recovery, all of it. This turns out to make the resulting agents significantly more robust because they learn what failure looks like and how to recover from it. The results on Terminal Bench 2.0 speak for themselves. The 32B model hit 27.4% accuracy, beating Qn3 coder's 480 billion parameters at 23.9% and outperforming Grok 4 at 23.1% and GPT-5 Mini at 24%. The 8B model jumped from a 2.5% baseline to 13%, a 5 times improvement from the data pipeline alone. The coding agent space has been defined by proprietary tools. Claude Code, Cursor, Windsurf, Devin, they all rely on closed-source models, closed training data, or closed agent architectures. If you wanted to build something competitive, you had to reverse engineer what these companies were doing, guess at the training recipes, and hope your results were in the right ballpark. NVIDIA just removed that guesswork entirely. The Nematron terminal release includes the models, the training methodology, the synthetic data pipeline, and the source code. Anyone, a startup, an enterprise team, a solo developer, can now train a terminal agent from scratch using a proven approach. The deeper signal is about what actually matters in building capable agents. NVIDIA's paper explicitly states that they focused on scaling model capabilities through targeted fine-tuning rather than building more complex agent frameworks. In their words, a smarter model inside a minimal framework beats a general-purpose model inside a sophisticated framework. That inverts a lot of the conventional wisdom in agent development, where teams have poured effort into elaborate tool-use architectures, chain-of-thought scaffolding, and multi-agent orchestration. NVIDIA is arguing that high-quality, diverse trajectory data is the more powerful lever, and a 32B model proving that against 480B competitors is a strong piece of evidence. Keep an eye on NVIDIA's GTC conference happening the week of March 16th. The company is reportedly preparing to announce NemoClaw, a broader open-source AI agent platform aimed at enterprise customers. If Nematron Terminal is the model layer, NemoClaw could be the full deployment stack, and expect the open-source community to start producing fine-tuned variants of these models within days. The 8B model in particular is small enough to run on consumer hardware, which means custom terminal agents are about to become very accessible. NVIDIA's release is a story about data, specifically how the right training data can make a small model punch far above its weight. The next story is also about data, but from a completely different angle. Instead of synthetically generating it, one company discovered that the data it needed already existed, captured over a decade by millions of people who had no idea they were building infrastructure for autonomous robots. Niantic Spatial, the AI company spun out from the creators of Pokémon Go, announced a partnership with Coco Robotics to deploy its visual positioning system as core navigation infrastructure for Coco's autonomous delivery fleet. The technology runs on something remarkable: 30 billion geotagged images crowdsourced from the phones of Pokémon Go and Ingress players over the past decade. Since Pokémon Go launched in 2016 and its predecessor Ingress in 2013, players have been walking through cities with their phones pointed at the world around them. Their devices capture detailed images of storefronts, intersections, building facades, doorways, sidewalks, the full texture of urban environments. Each image comes with metadata pinpointing the phone's precise spatial position. Niantic Spatial has used this dataset to train a model that can determine exactly where something is based on what it sees. Coco Robotics needs this because GPS is unreliable in exactly the environments where delivery robots operate. As Coco's CTO Brian McClendon puts it, the urban canyon is the worst place in the world for GPS. Radio signals bounce off buildings, get scattered by underpasses and freeways, and the blue dot on your phone can drift 50 meters from your actual location. For a delivery robot that needs to find a specific restaurant door or navigate to a customer's building entrance, that kind of error is a deal breaker. Coco's robots, roughly flight case-sized units that can carry up to 8 extra-large pizzas or 4 grocery bags, are fitted with 4 cameras. Using Niantic's model, they match what they see against the visual map built from those billions of player images. For each of over 1 million locations, Niantic has thousands of images captured from different angles, at different times of day, in different weather and lighting conditions. The result is centimeter-accurate positioning that works in the exact places GPS fails. Coco currently operates around 1,000 robots across Los Angeles, Chicago, Jersey City, Miami, and Helsinki. They've completed over 500,000 deliveries covering several million miles. Their next-generation Coco 2 bot, launched in late February, operates fully autonomously, no remote human drivers, and can travel on streets and bike lanes at up to 13 miles per hour, well beyond sidewalk speed. This is one of the most unusual competitive moats in technology. Niantic didn't set out to build mapping infrastructure for robots. It set out to make a game where people chase virtual creatures through real neighborhoods. But the side effect of that game, 30 billion carefully geotagged images of urban environments worldwide, turned out to be exactly the dataset that autonomous navigation needs. Niantic Spatial CEO John Hanke described it as a Cambrian explosion in robotics, and argued that if robots are going to share environments with humans without being disruptive, they need human-level spatial understanding. That's what this visual positioning system provides. Not just knowing which street you're on, but knowing exactly which doorway you're facing, which side of the sidewalk you're on, and where the entrance to a building is. For the broader robotics industry, this highlights a strategic question every company in physical AI should be asking. What datasets already exist that could solve your hardest infrastructure problems? Waymo built its own mapping fleet. Tesla uses its customer vehicles. Niantic had gamers do it for free. The data collection was a byproduct of entertainment, and the mapping layer it produced may end up being one of the most valuable geospatial assets on the planet. It's a reminder that the most powerful data flywheels aren't always the ones you design intentionally. The immediate thing to watch is how Coco's fully autonomous Coco 2 robots perform at scale with the Niantic positioning system integrated. The shift from remote human drivers to full autonomy is a major leap, and centimeter-accurate positioning is a prerequisite for that to work reliably. Beyond Coco, Niantic Spatial is positioning its large geospatial model as infrastructure for the entire robotics industry. So expect more partnerships with companies building autonomous systems that need to navigate human environments. We're at a point where the building blocks for AI, whether it's terminal agents running code or robots navigating sidewalks, are shifting from locked-down proprietary systems to open, composable infrastructure. The question worth sitting with is, what does the competitive landscape look like when the foundational data and training pipelines are available to everyone? If you want to stay on top of these developments, subscribe. We cover AI and tech news daily. See you in the next one.